both unmuted, and then you just need to turn on your mic for the
Okay,
house.
just this one.
Yes.
Okay, I'll wait till Yoni does this. Cool, thank you.
Okay, so welcome everyone to the last IQUIS seminar of the semester. It's my pleasure to introduce Dan Carney. So Dan Carney is like my favorite example of a person who's made the transition from formal theory to phenomenology in the most like awesome and ambitious way possible. So Dan trained as a string theorist at UT Austin, but has since been migrating gradually towards kind of quantum everything, including postdocs at British Columbia and Maryland joint with Fermilab. So he's now a staff scientist at Berkeley. I have intersected with him through some interesting ideas he's had with some of my collaborators on looking for dark matter using quantum limited sensors, assuming only gravitational interactions. And then today, Dan will tell us about an even more ambitious program, which is to detect signatures of quantum gravity in the laboratory using all the amazing tools of quantum metrology, for which I'm sure everybody in the audience is more familiar than I am. So Dan will be around both today and tomorrow. So if you haven't signed up to meet with him, I think there's extra slots in his schedule. He's just an awesome and creative person to talk to. So I strongly encourage that. Without any further ado, take it away.
Yeah, thanks, Yoni. Is this on? Yeah, sounds like it. Thanks very much for having me. I know it's like the last day or two of the semester, so I hope this isn't too dense. Yoni said to give a broad overview, and that has been my goal. So in particular, I'm going to give a biased overview of this kind of crazy world. So, this title, often people think maybe it's an error or I'm crazy or, so, there's a lot of controversy about this sort of general idea. And the goal of this talk has been to sort of be very cold-blooded and say just technically what is going on and what can you try to do. Let's see if this works. So, okay. So there's a couple different ways of thinking about this. So I'm from a high energy background, like Yoni said, and in high energy, a sort of classical way of asking about could you test quantum gravity would be to do some kind of particle physics experiment. So there's this nice paper, Freeman Dyson wrote this when I was in grad school, and it really kind of got me thinking about all of this. And so the title is pretty clear, is a graviton detectable? So, graviton is just the photon for gravity. If it exists, can you detect it? And this is a really beautiful paper. There's like a lot of, worked examples of a way you could try to make a detector that could detect single gravitons. And I'll talk a lot about the conclusions as we go. More recently, there's been like a very different way of thinking about these questions, which is sort of more in a quantum information perspective. This is John Bell, which is like, can I do something uniquely quantum mechanical using the gravitational interaction? So not necessarily directly involving, quantized radiation, but just something involving the gravitational interaction between two objects. So these lead to very different kinds of tests with very different technical challenges. So what I'm going to do is start by saying what I think you should view as sort of the null hypothesis in this world. And this is me being a really conservative, grumpy person. And then I'm going to talk about sort of classes of experiments. So first I'll start with sort of these radiation experiments on looking for graviton signatures. Then I'll talk about some tabletop proposals that have been put out. And finally, I'll just have a couple comments about things involving holography, which is an idea coming out of string theory. So this is the null hypothesis in a sort of pictorial language, but I think it's good for orientation. This isn't supposed to be derisive. So suppose I'm gonna ask a question like, is gravity a quantum mechanical degree of freedom? So what do you really want to ask? You want to ask questions like, can I take the gravitational field, put it in a state where it's superposed in two quantum states? Or can the gravitational field be used to do something like generate entanglement between two objects, just the same way that the electromagnetic interaction can entangle, say, atoms? So one way of sort of picturing that would be a cartoon like this. So this is, imagine there's some source mass, but this could be anything. This could be an electron, it could be something bigger. And a source mass, under Einstein gravity will cause some gravitational field to be sourced, and that's what this cartoon represents. So if you want to ask questions like this, you'd like to do something conceptually like take this source mass and say, superpose it into two locations. So this is the same mass just in two places. That's this double ket. And now under sort of baseline assumptions about how gravity could work, basically by analogy with how electromagnetism works, the gravitational field will come along for the ride and now be superposed along with the mass. So that's what these kets say. The mass is one place and the field is over here, and so forth. So you want to know, can I do this? And if you want to know that you actually did this in a lab, there's a further step you have to do, which is detect this thing. And that's sort of schematically what you imagine by having some test mass that would fall on this superposed gravitational state. So the question is, can you actually do all of this? So you can write down models where this works, and I'll show you one. The question is, experimentally, could you verify that this happens or test that maybe it doesn't happen? And the null hypothesis should be that this does happen. Okay, so this happens in electromagnetism with the Coulomb field, so it should happen in gravity with the gravitational field. That's sort of the baseline working assumption. But we have never measured this, so that's sort of the goal, is to actually check that in practice. So this is a little more technical. This is probably the most technical slide in the talk. But I just want to say this. I think people sometimes, especially if you're not working in high energy, are under a misguided impression that we don't have a theory of quantum gravity. So we do. We have one that works very well, and we have one that might work at all scales. So the one I'm going to focus on is just called effective quantum field theory. So this is just the idea that you can, in fact, take the gravitational field and quantize it just like the electromagnetic field. So until like the 80s, this was viewed as very problematic because it's a non-renormalizable model, but we now know how that works. It just means that your model breaks down in some regime. And in particular, it breaks down some very high energy density, which is totally irrelevant to all these tests. So in all of the examples I'm going to show, you can take gravity, just the usual Einstein gravity, assume that space-time is nearly flat plus small fluctuations. Those fluctuations are called gravitons. You can quantize this just like normal. It's totally fine. So this is the null hypothesis. Okay, so you're probably this is what's going on in nature, and we're just testing, could something go wrong, basically. So anything that's not this has to do something quite weird. You can prove basically that either the model will not have unitarity, so gravity will somehow be an open system, or Lorentz invariance has to be violated, or locality has to be violated, or maybe slightly more even exotic pathologies. So my personal priors is that almost for sure this is the right answer, but what you want to do is sort of be a little paranoid and think, well, what if something went wrong, and how can you test it? Are there any questions about that sort of high level starting point? Okay. So now I'll just move through a list of tests. So I'm going to start with radiation experiments because this draws from quantum optics, beautiful stuff understood in quantum optics. Yeah, and I'll go through this in a list. So everything I'm going to say in this section is based on a paper that should be up in a few weeks with Valerie Domche and Nick Rod, who are at CERN. So here's sort of in more detail what the null and alternative hypothesis will be. So this is a sort of like phenomenological way of looking at this. Here's the null hypothesis. I have a detector. Okay, the detector can be LIGO, it can be something else, it doesn't really matter, but it's some quantum mechanical system. And then if I quantize gravity perturbatively, I have some gravitons, so they're like free waves, they have a kinetic energy, and they have some interaction with the matter. So this is the gravitational field interacting with the matter. What's like a simple toy model for an alternative? I don't do this with gravity, so I still have a quantized detector, but now I just have some classical radiation field for gravity where there's no hat, that means it's not an operator, it's not quantum, but I will allow it to be drawn from a classical probability distribution. So this would just be classically random gravitational waves are available in the universe. Please. This is just the kinetic term. Yeah, it's quadratic in H. Yeah, I usually just think of this as, H box H. The usual kind of thing. I mean, we could talk in some detail. Okay. The key point is just supposed to be that here, this thing is a thing that has a Hilbert space. You can do things like superpose its state and so forth, and here you can't. You can just classically draw it. So that may sound like a weird starting point. So let me show you why we start with that. This is a classic quantum optics setup. So in quantum optics, so people used to argue about the photoelectric effect a lot. Actually, people still do. So the photoelectric effect is I have a piece of metal. The metal has electrons. The electrons we're going to assume are quantum mechanical systems. There's sort of like a ground state and a conduction band. And the photoelectric effect is the statement that if I shine light on this metal, the electrons can be excited from the ground state into a conduction band or fly off in this picture or whatever. And the photoelectric effect, you can make a detector with it by saying, well, if light shines on this thing and then an electron is freed into the conduction states, then I've detected a photon, or I've at least detected electromagnetic radiation. So a lot of times you'll hear in class somebody say something like the photoelectric effect proves that the photon is quantized. This is totally incorrect. Okay, so here's why. Here's what I mean by it's incorrect. I can take a pair of models like the ones I just showed you, one where I quantize the electromagnetic radiation, that's this guy A, which is just interacting with the detector electrons, which have momentum p. And then I'm going to compare this model to a model where I don't quantize the photon. I just have classical random electromagnetic radiation. So you can just open Sakurai and calculate the excitation spectrum for these photoelectrons in either of these models, drawing from either a classical distribution or a quantum state, and you'll get the exact same answer to lowest order in perturbation theory. So there's just a differential rate for the conduction electrons to be excited, and it's just given by some intensity of the light, which is either an averaged in an operator or classical. There's a theta function, which enforces energy conservation. And there's a phenomenological parameter called an efficiency, which just measures how much of the radiation is actually absorbed. So there's nothing in the photoelectric effect that can't be explained classically. Yeah. Yeah, so there maybe to be a little more careful, this is assuming some bandwidth, but so let me not try to overstate that there's nothing in the photoelectric effect that can't be explained. What I really mean to say, yeah, thanks, Paul. What I really want to say is that the detection of quantized jumps in the electrons has nothing to do with quantization of the photon. Yeah. H bar is going to be 1 in this talk, sorry. Yeah. It's just the frequency of the wave. That's just not correct, sorry to say. I mean, you can literally just compute from this and you'll get this. Probably this gap is going to be expressed as a frequency. I'd have to think about it a little bit. Sorry. This. Yeah, there. That'll probably do it. This is the gap in the electrons, right? So you can put an H bar in there. Yeah. This is actually just a beautiful little piece of an appendix in Mandel and Wolf. This is definitely not my observation. So this is sort of the basic claim. Okay, so there's a lot of effects if you see quantized detections that you can explain classically. So there's then a long story about which ones can't you explain classically. And so, Paul maybe gave an example. Let me focus on another one that we've been thinking about. So how do you test non-classicality in the electromagnetic radiation? Here's one way to do it. You can look for counting statistics to obey certain conditions. So there's a way to formulate this as follows. So I imagine in the quantized picture, I take a mode of the radiation field, and I'm going to write it in terms of coherent states. And you can always write the state in this form where alpha is a coherent state, and I can write an ensemble-looking thing. Rho is just an integral over all the coherent states with some weight. and the sums of the weights have to be 1. So you'd think this looks like a probability density. But it is not always. So if this P of alpha is always positive, this literally is just a classical ensemble of coherent states. Okay, and you can actually show in some detail that you can always find some classical PDF for the radiation field, which will explain anything you're going to see in terms of photon counting rates. On the other hand, it was observed a long time ago that P is not actually always positive. In quantum mechanics, you can find a state. So for example, a squeeze state or a Fock state has the property that P of alpha can be negative in some region. And so then what you can do is you can find an observable that you can show cannot be explained by a classically random model. So a specific one that's very beautiful, you can do it in optics, is called sub-Poisson statistics. So that just means I take the photo count rate, like let's say n, versus the variance in the photo count rate, and I compare them. So Poisson statistics is that the variance in the photo count rate is equal to the average. So that's shown here. Super Poisson means that this is bigger than the average, and sub-Poisson means that the variance is less than the average. So there's a formula you can work out for this quantity, which is given in terms of an integral over this Glauber distribution P, okay, times a positive definite quantity. So this left-hand side, if P of alpha is always positive, this thing is also always positive or 0. So in other words, you can only see Poisson or super Poisson statistics. However, if P of alpha is negative, for example, in a squeeze state, you can actually get sub-Poisson statistics, meaning that the variance is lower than the average. And that's the kind of thing you're going to look for, where you can show you can't find a classical PDF for it. It's a little bit subtle. So are there questions about that? Yeah. Oh, sorry. It's just my notation. So alpha is a complex number, and on one equation I noted that, and one yeah, thanks. Yeah. It can. Yeah, it's because the alphas are an overcomplete basis. So yeah. So yeah, I should say that there were experiments looking for this in optics. Within the past couple of decades, it took a lot of development. Why? One reason is because you need a laser that can make the state, so like a squeeze state or something. The other thing is that there's a detector efficiency sitting on this right-hand side. So if you have this is a number less than or equal to 1, this eta. So if you have a high efficiency detector, you can imagine trying to see a deviation from 0. But if you have a low efficiency photodetector, this is basically always going to look like 0, and you'll just see Poisson statistics. So let's now try to apply that to gravity. Okay, so first I have to show you how you can count gravitons. So there's many ways of talking about counting gravitons. Let me show you one that I think is cute. So this is an experiment at CERN. This is called CAST. It's an axion haloscope. Doesn't matter. What it is for the purpose of this talk is it's a big magnet. It's a 10 Tesla magnet with an X-ray photodiode strapped to the end of it. So why you would build that is, it's particle physics, but it exists. And it was actually observed by Dyson in that old paper that you could use this to detect gravitons. So the way it works is the following. You can show that just in perturbative gravity coupled to E&M, there's an amplitude for a graviton in the presence of an external magnetic field to convert into a photon. And it has to conserve energy, so a graviton of some frequency converts to a photon of the same frequency. So people have recently kind of observed that you could use this as a gravitational detector, including Yoni's been involved in this work. This particular example is extreme in the following sense. So this object detects in the X-ray spectrum. So it's super high frequencies, like 10 to the 18 hertz. And it can really count single gravitons in the following sense. So let's imagine I send a beam of intense, very high frequency gravitational radiation at this thing. There's a probability for a given graviton to convert to a photon, and it's given by this simple mixing formula, which we don't have to work through it, but gives you some number. And the number says that the probability for a given incident graviton to convert is of order 10 to the negative 33. And that's set by the B field and the baseline. Okay, that's the right response. However, so you think, okay, this is just like the stupidest detector ever. However, If you look at the number of gravitons in a gravitational wave, you can get an astronomical number to multiply this by. So for example, if you take a strain that's sort of a reasonable LIGO-E strain and integrate it for 10 milliseconds, what you'll find is that actually the number of gravitons is sufficiently large such that this multiplied by this is bigger than 1. So in other words, in a 10 millisecond pulse, you'll actually detect a handful of gravitons in that language. So that's pretty cool. Now, I want to emphasize that there's no known sources for gravitons at 10 to the 18 hertz. So, I'm not trying to say that someone's going to go do this. However, just at the level of detector physics, this is a sort of proof of principle that you could, in fact, detect a single graviton or a few gravitons. However, I think what I was trying to show in the previous couple of slides was supposing you did it, it doesn't really show you that the metric was quantized in the first place, because I could just as well explain at detection by saying there's classical gravitational radiation coming and causing clicks in the photodetector. So what it's because the photon detector at the end of this thing is in X-rays. Yeah, you don't usually see X-rays in frequency, but that's okay. So then the last question is, okay, maybe I can detect some gravitons. So can I detect something quantum about this, like sub-Poisson graviton statistics? And the answer is definitely not. Okay, so the reason is what I said earlier about detector efficiency. So if you look at this formula for the photo counting statistics, I mentioned earlier that there's this efficiency on the right-hand side, and if it's small, then this will always look like 0, and you'll see Poisson statistics. And here, what I just said is that the efficiency of this detector is 10 to the negative 33. So this is astronomically close to 0, and any graviton clicks you happen to get lucky to see are always going to be Poisson distributed in the data. You can ask an interesting question if you're like a theorist: is could I even in principle build a detector that could do this? And the answer is maybe. Okay, so you need a very, very large magnetic field, like 10 to the 13 Tesla, or you can make a very long baseline, like the size of the galaxy. But there doesn't appear to be a rule of physics other than budget constraints that would disallow this. Okay, so I think that's kind of an interesting claim. It could have gone down differently, and you could have proved a theorem that says you could never detect some quantum signature of gravitons, but that doesn't seem to be true. Nevertheless, as a practical way of testing quantum gravity, this is not what you want to do. This is maybe a little technical, but just if that cast example is weird, there's a very similar story in LIGO. So if you make a detector like LIGO, and you're measuring in amplitude instead of intensity for the detector people out there, there's a totally analogous statement, which would just be, I'd like to detect something like, so this is a formula for the variance, so the wiggles in the gravitational waveform, as a function of the state of the radiation you shoot in. And you can make a similar looking formula to that sub-Poisson counting statistics that says the variance in this waveform is given by a positive piece plus a little piece involving vacuum fluctuations, except this positive piece could be slightly negative in something like a squeezed graviton state. And then you can ask the same question: could I detect a small negative piece in this right-hand side? Okay, well, the answer is no. The reason is because to detect a small negative piece, I have to beat the vacuum fluctuations of the graviton shot noise. And the vacuum fluctuations of the graviton in units relevant to LIGO are strains of order 10 to the negative 60, whereas the detector operates at 10 to the negative 20. So you're just many, many, many orders of magnitude from seeing any quantum signature in something like this. Forget it. Let me say this actually, so I can stick to my slide. So there's been claims that you could look at the microwave background and look for tensor fluctuations. You can maybe do that. Certainly you can look. Supposing you found them, would it prove that the graviton was quantized in the early universe? The answer is no, for the same reasons as I was just saying. If I see tensor modes in the sky on a Gaussian spectrum in the 2-point function, you can similarly explain them with the stochastic classical model. There is an interesting idea to look at 3-point functions. This is rather technical, but anybody who's really interested in this could ask later. Okay, so recap of sort of the radiation test. So, I think maybe surprisingly, yes, you can detect single gravitons. And in a way, there's kind of a simple way of thinking about that in terms of just how measurements work. However, I really want to emphasize that just counting gravitons, quote unquote, counting gravitons, meaning seeing a data stream with clicks in it, enough to say that the field is quantized. You really could explain it classically. To rule out a classical explanation for the field, you would need something rather more difficult. In particular, you need a source of non-classical gravitons. Who knows where that's going to come from? Second, you need a high efficiency graviton detector, and this is extremely prohibitive to try to construct. Please. Maybe I should have said, so string theory at low energies is quantized as an effective field theory. That's actually one of the reasons it's an interesting model. So it has quantized metric fluctuations and all that. Yeah. Yeah, it's an interesting question though to ask. Is there anything you could rule out by like counting these clicks? I don't know of an example, to be honest. But I don't have a theorem that says that there isn't one. Yeah.
So difference between, random so there are reasons for going in the direction of sort of counting currents with like dulling quality things.
I would say that my conclusion from this is that this is the wrong thing to do, and the better thing is the Bell tests. Yeah, that's exactly. So I'll in fact next do the Bell tests. So before I move into this totally different world, any last questions about? Yeah. It's certainly not a proof that it's quantized. Yeah, I think, this is now it becomes to taste, right? So, how twisty is the knot that I have to make to believe this? Okay. Good. All right. So yeah, so Yoni kind of teed that up for me. So Mike, one conclusion of that is if you want to test the quantization of the field, I don't think you should do it by looking at gravitons. At least currently, we don't have anything like a good idea for that. What you can do, however, thinking about tabletop experiments, and this is a little more subtle. However, it might actually work. So, all right, so there's sort of two classes of these. So there's experiments where you would look for entanglement generation by the Newton interaction, so non-relativistic Newton interaction. And then there's a sort of more subtle version where you instead look for coherence in the interaction, and I'll define this as we go. So this is a cartoon of, again, the null hypothesis versus some alternative kind of hypothesis. So the null hypothesis is, again, gravity is quantized perturbatively. It does everything E and M does. So in particular, from a high energy way of thinking about it, you can say there's gravitons, they are exchanged between matter, and there's virtual graviton exchange, just like virtual photon exchange. In a more low energy way of thinking about it, this just means that there's a Newton operator, an n-body Newton potential in the Hamiltonian. So just two masses talk to each other where these x hats are position operators on the masses. Okay, so what could possibly be different? It's a can of worms to make a model that is not like this. Qualitatively, what they look like tends to be things like this. So I'll explain the circuit in a second. But what you're typically are looking for is a model like a semi-classical model, where instead of the two position operators talking to each other quantum mechanically, one is sort of projected into some classical information like an average, and then it talks to the other mass. So this is a two-body entangling operator between each pair of masses. This is a one-body operator. This is just a number and then an operator. So this in particular generates no entanglement. To actually make a model with this behavior, always in all known examples, and I think there's now a theorem that says this actually cannot arise in a coherent fashion, meaning there's always going to be some bath that implements this interaction. So there's gravity is not just a simple field that you can integrate out. There's many weird degrees of freedom living somewhere that you can't see. And that's what the circuit is supposed to represent. You imagine there's these two masses, which are this S1 and S2. And instead of talking to each other directly, they talk to some bath, this A1, A2, and the bath sort of feeds back information onto the masses to implement this interaction. So this is a toy model based on sort of measurement and feedback on a computer. But all models tend to have this behavior that there's some bath and therefore some loss of pure unitarity. This is not a unitary channel on the two masses. So the question is, how can I rule out everything like this? Because these are horrible and it would be terrible if nature worked this way. So first I'll talk about this idea of testing the entanglement generation. So this is a cartoon of how this works. So this is just imagine I have two massive objects, and you could think of these as sort of mesoscopic, microgram, even to gram scale objects, which are just sitting somewhere in a lab or falling. And I'm gonna be able to do preparations and measurements on each of these. And so you're asking, like, can this Newton interaction entangle these objects? And then can I observe that, for example, by looking for something like a Bell violation in the joint state of the two objects? I mean, are there questions about what I mean by these words? Sorry, this is not everybody's stuff. Okay. I just mean that you prepare this in an initial product state, and then you get some non-product state. You're asking, can I detect the presence of a non-product final state? There's like, I don't know how many proposals for doing this, and there's a pretty good list of them in this paper as of 2021, if you're interested. So just to kind of highlight what would be the alternate prediction. So in one of these models where there's like a classical gravity model, gravity is not entangling, it just means that there's no entanglement. So in other words, if you can observe entanglement in the two-body system, you rule out everything like this by construction. That's why people are interested in this. So yeah, quantization predicts that there's entanglement. Any of these classical models will predict an unentangled final state, and that's the goal. Okay. So on the circuit diagram, the way it works is the two masses, this S1 and S2, they just don't talk to each other by a two-body operator. So how hard would it be to do an experiment like that? It will be hard. This is the famous example. This was really the proposal that I think in practice started a lot of this, although there were some earlier versions. So this is a proposal that came out of a big supergroup. So got proposed at London. There's people all over the place involved in this paper. So the proposal here was to take an NV-centered diamond. Okay, so this is a microgram scale diamond. The NV-centered just means that it has a spin. So if you're familiar with NV diamonds, great. If you're not, just think of this as a really big neutron. Okay, it's a neutral object with a spin that couples to the motion. So in particular, you can take this microgram scale object, send it through a Stern-Gerlach, and put its center of mass motion in a superposition of two locations or two paths by just putting the spin in the same superposition. So this is, first of all, a proposal to make a microgram scale object superposed in two places, already a non-trivial goal, to put it lightly. What you'd further then like to do is take two of these and have them interact gravitationally. So the proposal was do this twice, separated by about 1 millimeter. And what you look for is the Newton interaction to cause some phase-dependent, some path-dependent information in the phase on these 4 different paths. However, you can show, on a piece of paper, if you put the Newton interaction, this thing falls for some time, it'll generate some observable amount of entanglement, and the amount of entanglement is encoded in a differential phase. So this is the full evolution. Then some paths, it's split up into the 4 paths, and there's some sort of differential phase shows up, say, on one of them if you organize it right. So how big is the phase? The phase is given by a very simple formula. This is just a Newton potential, g Newton m squared over a distance. There's a factor of the superposition length over the separation, and then there's a time, which is the time you have to let these things interact to build up the phase. So you can observe this if the phase is sort of order 1-ish, maybe a little bit smaller, but not a lot smaller. And so to get an order 1 phase, the numbers are not easy. So you want sort of, the way I parameterized it here was nanogram scale diamonds superposed at a micron distance, meaning the distance between these two paths is a micron, placed 1 millimeter apart from each other. So this is not drawn to scale, sorry. But then the killer is you need to integrate for a second. And that's really the hard part here. So what this means is you need to take these large nanogram scale objects, drop them, keep them quantum coherent for an order of a second while you build up this phase. So in other words, if a gas particle hits this while it's falling, this is over. So the amount of gas pressure that's tolerable is not reasonable here. You can try to massage the numbers, and people are working on this. It may actually be doable, but it is hard. Yeah, Yoni. Yeah, you can increase the mass, and indeed. So the question is then how does the decoherence rate typically scale with the mass, which is also not good. But yeah, this is not optimized for sure. This is just some numbers I put in. Yeah, the NV in this example is that's it exactly. So in principle, you don't need to do many components of this. It doesn't need to be an NV. You don't need to do this with spins. They don't actually both have to be superposed. Conceptually, this is pretty clean. In particular, because you can read out the entanglement by just doing a literal Bell measurement on the spins. Okay. So, like I said, it may be possible, and people are really working on this very hard to do all the elements of this. And I think I have some optimism that in my lifetime something like this will get done. However, it's kind of left room for thinking of versions of this that are easier to do. So this is something we thought of, and there's variations on this. I just want to show it because I understand this one the best. Instead of looking for the entanglement to be generated, you can look for something a little simpler. So we call this a coherence test. So here you're testing something about these specific non-coherent models. So I said earlier that in any model where gravity is not going to entangle, there's actually a theorem now that says that model has to be non-unitary, it has to be non-reversible. And so that pretty much tells you that there's always going to be some bath laying around, and that bath will cause noise. So on the circuit, what this means is that as time is progressing, you're trying to have the gravitational interaction build up, and some information is getting lost at the bath. And what that'll do is it'll degrade the quantum state of a mass. So you can make a test specifically of that. So I'll show you what this looks like in sort of real life in a second. But sort of schematically, you can imagine now I just take a large source mass, for example, a pendulum, and I just want to use this as a source that I'm not actually going to look at its state. I don't have to make a measurement on this thing. I just use a very sensitive gravimeter to monitor its field as a function of time. And I look for noise in that Newton interaction. So this example is an atom interferometer. So this is an atom superposed in two locations. This is a very good gravimeter. In particular, it's a gravimeter you can put nearby a small source mass. And there's particular signals you can look for. So one that we proposed here was with a pendulum, you can make the Newton potential oscillate at some frequency and look for it to have some noise that's periodic in time, where what you would actually see mechanically is a loss in sort of phase visibility in the atoms. So then the goal would be, so I should say, in particular, there's a signal where if gravity is coherent and there's no noise in the lab, if you let a pendulum swing for its period, and you look at the state of the atoms, they'll have some initial condition, and then under a coherent interaction, after half a period of the pendulum, it'll come back to the same place, and the state of the atom will itself return to exactly its initial condition. So there's some perfect periodic thing in the visibility in the atoms. On the other hand, if the interaction has some noise it's generating, this won't be true, and you'll lose some contrast. So you can look for the deviation between this perfect periodic revival signature and a decaying periodic revival signature. But now it becomes quantitative about, okay, how much can I differentiate this loss versus loss from my actual experiment, which has noise, and it's a little hairier. However, these are experiments you can just go do. So this is a proposal. This is how it could look in real life. So this is the same cartoon I just showed you in a slightly more fancy way, where you'd imagine taking atoms. So these are atoms loaded into an optical lattice. This is actually how it works in the lab in Berkeley, in Holger Mueller's lab. You put the atoms, you can fix them to a location. They can be kept quantum coherent for about a minute now, which is quite impressive. And then you can imagine some mass, for example, hanging a torsion balance next to the thing that can be tuned to have whatever mass and frequency you really want. And the statement I want to make is just that the signature you're looking for at face value is the fact that this fringe visibility goes down and then back up. So how big is this contrast change? So this is again a phase. So this is an order 1 number you're looking for. There's some formula for how big the phase shift is in terms of the gravitational interaction, and so various parameters, meaning the number of atoms you're putting in the trap, the solid density of the mass here, the temperature of this mass, how far you put them apart, and so forth. And with relatively benign numbers, you can really start seeing this periodic signature and measuring it in some level of precision. So the numbers I put in here, this is at room temperature with a millimeter separation. That's fine. This is a sort of a large number of atoms, but you could just make this up with a number of runs, and then the coherence time you need is already been achieved in Holger's lab. Oops. So again, I just want to say, this is a less robust test. If you see this visibility shift, you will not rule out all classical models, but you start ruling out some, and then it becomes kind of a race to classify them and show that you ruled them all out versus doing the entanglement measurements. Yeah, please. Yeah, that's right. So if gravity was noiseless, you would modulo actual noise, you would get a perfect revival, and then you're looking for deviations from that perfect revival. And you can only distinguish those versus obviously the real noise in the experiment. Okay, so this is a slightly technical tangent. Now, so I've sort of outlined these classes of tabletop experiments that have been proposed, and then people often ask, what do these have to do with the graviton you started with? It's a little subtle, but I want to put this on one slide just so people have heard this. There's a pretty direct relation. So you can prove the following thing. Imagine I have a model that has the following sort of simple assumptions. It's unitary, it has Lorentz invariance, and I put in by hand that it has the standard, coherent Newton potential as a two-body operator that entangles. You can actually show that this model then has to have quantized gravitational radiation. And so the idea would be, okay, well, if I can all these properties, I don't have to detect gravitons or sub-Poisson gravitons or test these. I just want to give one slide showing how this argument works. I'm happy to show a lot of details about this. But basically what you do is you analyze how these experiments actually work as a scattering process. So if you look at these experiments, you have a mass here, that's this line. You have another mass here. You're trying to look at their interaction through the Newton potential. And there's some experimentalists who have to do things like control the particles and measure them. So if you analyze this sort of abstractly as a scattering diagram, where you put in this Newton interaction, then under assumptions about under the assumption of Lorentz invariance and unitarity, you can show that there has to be corresponding diagrams where gravitons are emitted. And so this just comes from this is a technical thing for any high energy people. You can just take that diagram, look at the imaginary part, check if you can satisfy the optical theorem, and convince yourself that the only way the optical theorem for this diagram, this process can be satisfied is if there are final states with these mediators going out into free space. It does, good. So that is why I use this word quantized gravitational radiation. So what you actually learn is that the coupling has to be root G Newton times M, and it has to be a boson, otherwise you're going to mess up the statistics on the right side. But it could be spin anything integer. Say that again. It does not mean spin 2. Yeah. So you could do a version of all of this where it would have to be spin tube. For example, if these lines are null, so if you did light entanglement, then you can start thinking about the spin. But yeah, at face value, you could actually be measuring a fifth force that's quantized or something. So that I'll take that. That's fine. Okay. Good. So that's sort of again, the claim is supposed to be that you can get at the presence of the graviton by doing these non-relativistic experiments, but it's conditioned on some things that you have to assume. All right. So said all this already, and then I just wanted to have my 2 slides on holography and we'll be done. But the entanglement tests rule out everything that's not entangling. So they're the most robust, but they're also the hardest. The coherence tests are easier, but they only rule out specific models. As far as we know, but there's a big theory problem to classify these kinds of models. You can get at the graviton, and then the big open question to me is actually, can you classify all of these models where gravity is non-entangling or incoherent somehow? And there's been some recent work, so out of John Oppenheim's group in London, and out of this is just a guy, Akira Matsumura in Japan, who's been writing a lot about this in the relativistic case. Okay, any last questions on the tabletop? And then I'm going to do 2 holography slides, and that'll be it. Yeah. Definitely. By design. Yeah. Yeah, I can't do nonlinear gravity, so everything in this talk is linearized. All right, so this I like to put in. There's one thing that's a little clickbaity and one that's, well, still pretty clickbaity, but okay. So the first one is this holographic simulation idea, and then the second one is a comment on the searches for so-called holographic noise. So holography, if you haven't heard about this, holography is this idea, and it has been around in gravity for a long time now, which says that the entropy in a volume doesn't scale like its volume, it scales like its area. And this has all these things to say about counting of states, and there's a whole story. But people have been looking for signatures of that in real life for some time. And recently there was this idea that you could make a wormhole on a quantum computer. This got really lampooned, and I think that was reasonable. Okay. So, this is I kind of feel bad throwing these guys under the bus, but they didn't write the paper, they wrote the comment. Okay, but the paper was in Nature. It said that they made a wormhole, and okay. So it's a little overblown, but I want to emphasize, just to push back on that a little bit, that there is something non-trivial here. So what the idea would be, you simulate something on a quantum computer that you can predict the effects of it from a gravitational calculation, and that's really cool. So you're not going to actually test the physical gravitational field. You don't make a physical wormhole in the lab. You make something on the field theory side of the duality. However, you do test the duality. So you're testing whether or not you can actually predict what's going to happen on your computer using a gravity calculation. So in particular, there's like a really non-trivial thing you could try to do, and people have been talking about this for longer. This is not my observation. What you really like to do maybe is something like the following. Imagine you could do a quantum computation where it has 100 qubits involved. You cannot predict its outcome on your laptop or a supercomputer. However, you could predict the answer using a classical gravity calculation in string theory, and that would be pretty cool. Then you can argue about how many qubits you need to be there, and okay. Nevertheless, I think this is the actual thing that will be done pretty soon, probably, and will be cool. And I want to emphasize that this is not like some totally wild, novel thing. People have been trying to do stuff like this for a long time, using the string theory side to predict something in flat space, not string theory. So there were ideas of heavy ion collisions. There are things in just pure condensed matter about diffusion coefficients in metals. And this really is in the same category. Now I want to say something I actually know, which is this idea of looking for what's called a holographic noise. So holographic noise was this idea that really originated in these papers by Craig Hogan in the noughts. And then there was an experiment actually done at Fermilab called the holometer, maybe you've heard of. So, I don't want to defend this too strongly, but here's the idea. So the idea is that, imagine I take LIGO or some gravitational wave detector. So this is my cartoon of an arm of LIGO. It's just two mirrors. Gravitational wave comes through, distorts spacetime, so on and so forth, causes the mirrors to have a slightly different length between them, and then LIGO reads this out. So you can ask a question like, if I quantize gravity perturbatively like normal, and I ask what's the noise in LIGO due to the vacuum of gravity, it's pretty straightforward to calculate this. And here's the answer. The variance in the path length. So this is 4 kilometers in LIGO, and you're asking what's the deviation from 4 kilometers just in vacuum? The answer is given by the Planck length squared times some stuff that involves an ultraviolet cutoff and a log. But you should think of this as just order 1 for this talk. So what this basically says is that the variance in LIGO from vacuum is ordered the Planck length squared. This is really small, so the Planck length in SI is like 10 to the negative 30 something meters. So you will not observe that. What these people have sort of suggested was that, okay, well, and maybe due to some mysterious holographic effect that nobody has said what exactly it is, the scaling could be different. And there's some kind of infrared scale that shows up. And the only scale you kind of have in this problem is the baseline of the experiment. So roughly the claim would be that this formula is replaced by this formula, where the variance due to the gravitational vacuum now becomes of order, not the Planck length squared, but the Planck length times the length of the experiment. Now let me just bury all the uncertainty in some coefficient, which maybe is order 1 and probably frequency dependent in some unknown way, and none of these people specify it. But the idea has been that, okay, if the length is a kilometer, order kilometers, you multiply by the Planck length, you actually get an observable number. So this would predict a variance, say in LIGO, of order 10 to the negative 16 meters, which is actually 3 orders of magnitude above LIGO's noise floor. So this is very observable in LIGO. So then you have to start arguing why you didn't see it, okay? And that's a whole story. But you can imagine this frequency dependence or whatever. So I just want to put this out there because people are still talking about this. Catherine Zurich and Eric Verlinde wrote a paper a couple years ago with a sort of rehashing a variant of this. And there's an experiment at Caltech that's now being built to actually look for this at megahertz. And I just want to emphasize that there is a EFT calculation you can do. It gives you an answer. The answer is you will not see the effect. So then anything like this is a violation of effective field theory. That's the way to look at it. The idea here is, whether they say it this way or not, that holography predict they want to look for a violation of effective field theory, which they would like to ascribe to holography. It's not actually super clear to me which part of EFT rules it violates, but that's maybe a dinner conversation. Please. Correct. Yeah. Or at least no one said anything about photons, which is probably for the better. Yeah. Okay. That is it. So sort of my outlook on this field. So I said this is a biased overview. My view is the following: that the tabletop experiments are a thing that are going to happen, that are already starting to be built. They can do things. They can rule out sort of these non-coherent, non-entangling models. We'd still need a classification of those models. That's a really interesting theory problem. Measurements of quantization in the radiation field itself. You can detect things in the radiation field, obviously, like it does all the time. But can you detect quantization signatures? Certainly anything you start writing down, the answer is just no. It's not going to be possible. That's all I really want to say here. So holographic noise would be cool, obviously, if you found that would be quite wild. But what's really needed is a model. And in all cases, I think there's a real nice open space for designing experiments that can actually work. I think that's all I want to say. So thanks very much.
Awesome. Thanks for the great talk. We got plenty of time for questions.
So, in the terms of the goals listed here, I don't know of anything. And the reason I say that is because, yeah, there will be curvature, but it's just sort of this background field. And what here, all these you're trying to look for is something where you can put the gravitational field itself into a quantum state. So you need control over that. That said, I don't want to say anything too strong. There are things you can learn by doing measurements in strong field gravity for sure. But I don't know if you can, it's not obvious to what extent you could use it to test the quantization of the gravitational field itself. That's a good question. You can test things like, so there's a famous experiment done on Earth, which is called the cow experiment. So the cow experiment is you take a neutron beam, you diffract into the two places vertically over the Earth, and then you interfere it, and you measure the phase shift caused by the Earth's gravitational field. You could imagine doing that in stronger fields with higher gradients or with lighter probes, or you can test that for some reason only work with the neutrons on Earth, things like that. At a fundamental level, I personally don't know what you would probe. Yeah. Paul. There are quite a few electrons. Yeah. So for sure, in principle, yes. And then there's a quantitative question of how much mass actually is moving around. But yeah, there's nothing, GR couples everything equally. So there's an acoustic version of that, which is this thing done in Zurich last year. So they have a chunk of metal and then, I forget what let me not say metal, some solid. And you can put a phonon and superpose it in counterpropagating acoustic waves. And for sure that would count. So, there it's with the lattice as opposed to the electrons, but same idea. Oh dear. Yeah. Oh, did I actually put an H bar in somewhere? Yeah, okay. So the answer is no, because H bar is 1, but if you want to think of it that way, yeah, so I'd have to backtrack to figure out exactly how these H bars work out. I think what you're really winning here is that you're doing a small velocity expansion. And so you can integrate, if you want to think of it that way, you're integrating many virtual gravitons. I don't know. Yeah, let me punt. We could digest that later. In SI units.
No more questions. Thanks, Dan, again.